All right, let's get started again. It's a good thing we took a break. Over the break, I was alerted that, hey, I made a blunder up here. Didn't anybody see what I did wrong? One person did. Yeah.
Were these questions that were on the test?
These are all past exam questions. So if you're looking, a lot of times when you're doing like homework, you say, oh, he couldn't possibly ask me this. And that's true for a lot of them. You can kind of guess that. But these are his questions. So, yeah. Welcome to college.
Can we rig the curve somehow?
If a lot of people are doing badly, he will be a little more generous with partial credit. But he holds to the curve pretty tightly. Sometimes he relaxes it a little bit, but he's really generous with partial credit. But yeah, expect that, these are the harder problems. I am showing you a number that are more difficult, but they are things that students have faced. And so hopefully we'll do a few of these. You'll feel a little more comfortable, and if he does anything like that to you, you'll know right where to hit it. Okay, I made a mistake in here. This is in the y motion. Shouldn't that be v naught in the y? V naught sine theta?
Yeah.
Okay, and I was just, now what I had done is I had this thing worked out, so I think the numbers work out well. It's just that my brain left my skull for a moment there, and I put this as a cosine, as though it was the x term. So you got to watch that, and I'm sorry I didn't catch it. I don't mean to make things any more difficult than they already are. But let's just kind of maybe read this, but let's kind of deal with this. If we fire one projectile, it's going to go on a parabolic path and hit over here. This other one is going to shoot up, and we want to hit that one. This is going to fire just straight vertically. So we've got two projectiles, projectile 1, projectile 2. Projectile 1, we want to write its equations of motion. So we start off with the x, and here I do want v initial times the cosine t, and of course there's no acceleration, so the time that it takes for this thing going up there, but basically in the x motion, it needs to go 50 meters, and I can get the time that it takes to go 50 meters. I take the x term, I set the initial is 0, I set the final is at 50, and I can go ahead and solve for t1, and I get 1.728 seconds. That's the time that it takes to get down to here. That's also in the y motion, since they're independent. The time that it takes to get to this point, this intersection between these two, that would be the time to that. It also has the y motion. I want to be able to get, well, where in the air does it hit? I know that the x is at 50. Now what's the y? So I want to solve this y. I can take that by taking the time in the x and substituting it in the y. And I've got this thing, and again, I apologize, this should be v naught times the sine of theta. So this should be the sine of 50 degrees. And again, I believe the numbers still work to the best of my knowledge. I've run this before and used it with other people, and then nothing's come up. So again, I think I just copied it wrong and left my mind. This is, I'll put in this t, and then I get this 44.92. That's actually the height above the ground where this one would be, where it crosses paths with this other one that's going to fire straight up. So that would be the height. Now projectile 2, this one is a little simpler. All it's doing is going straight up. I don't even need to worry about the x term. The x term is going to be at 50 meters along with that. Then I want to do the y motion. So I do that. and I want to set the intersection of y2. That's y2 is this projectile, y1 is that projectile. I want them to be at the same place. That 44.92 is where they cross. So now I want to figure out how long does it take for this one going up to get to that point. So that's what I'm calling T2. So I take the y2, it's got to go up to 44.92. It started from the ground. It has this velocity straight up, 90 degrees, 45, so that's 45 up. It's got 1/2 gt squared. And we do need to use the quadratic equation where we get two solutions. I get one at 8 seconds and another a little over 1 second. Now, you say, well, two solutions through that point. Now, this thing can go up, it can get to there, so I would suggest that's at 1 second, or a little over 1 second to get here. And then it's going to go straight on up till it stops and is going to fall back down and is going to get here again at 8 seconds. Okay, so this is how long it takes from when we fire this thing to when it gets there is going to be a little over 1 second. Okay, so now the question is, how do we time this thing? Explain how to fire the two balls so that they hit in the air. Okay, hint, there are two answers. I'm getting to the two answers right there. Okay, so consider that if projectile 1 fires first, that's this one, you're going to fire this thing, it's going to come down here. This guy's got to sit and wait a little bit because it's going to take 1.7 seconds to get down here, and he only takes 1.1 to get up to it. So he wants to wait a little bit. So it's going to take the time from this one minus the time it takes to get up to him. And so he needs to delay his firing. So once he sees that guy fire, he wants to fire at 0.588 so that he hits him going up. Okay, the second solution would be, how about if you fired projectile first? So he fires this off, and you want to hit it with this one. Well, this one still takes this long to get there, but the one going up could, again, go all the way up and come back down to hit it, and that would be this at about 8 seconds to do that. So if projectile 2 fires first, projectile 1 fires, it's the difference. It's going to take this long to go all the way up and come back down to that point, minus the time that this first one takes, and so you have to wait 6.32 seconds. And the guy that waits is actually going to be this guy. Because 8 seconds to go up to back here, he's going to come back down, and this guy only takes 1.7 seconds to get there, so that's why we subtract that from the 8, and so projectile 1 needs to fire this long after he first sees this guy fire. Is it making some sense? It's things you definitely need to think through. Okay. But is this an exam question? Yes, it was. And he's even gotten worse than this. Here's one. How about 2 cannons? And this guy's fired, they're at different angles, different velocities. They're separated by 3,000 meters. I think what I'm going to do is just kind of talk you through a little bit of the setup. It gets pretty messy. In fact, he says, solving the equations can be long and is important, but with limited time, the majority of points will be setting up the system of equations. So you're going to lay out the pieces of the puzzle for him. Okay, so again, kind of look this over, just kind of he's got it pretty well summarized with this picture up here. So we need to talk about, again, 2 projectiles. I've got, or cannon number 1 is going to fire. and then we need to fire this other cannon, and they're going to intersect somewhere. Now, the one we just dealt with, it was kind of simple since it was a straight line. We just needed to intersect with that. This is considerably throws a tight one in here. We've really got two parabolas, and the point where they're going to hit is that intersection point. So I'm coming back to the same basic strategy of setting up in a mathematical equation for that, a parabola, and a parabola for this. See where they intersect, and that's again where they need to collide or intercept. So this cannon number one, I can't put an origin in both of them. So this is a little bit of a twist here. So I've got this one. This is sort of like in standard configuration, so this should look familiar to you. We do the x motion. X is equal to the velocity, angle, time. We can solve for that time. Of course, that's in terms of x1. Okay, so again, don't be bothered by the fact that I don't have a number for that. In principle, this is equal to t1, and that's going to go into the y equation. And we can simplify that, and we end up with y1, and I do some of the math here, just get it down to simple numbers. y1, we have this and an x1, and we have an x1 squared. So this is the motion. This is actually the parabola for this projectile. And let's look at this other one. Now, this other one is not firing from the origin. Don't be particularly bothered by that. We basically will set it up the same way, except it's already starting from the origin at 3,000 meters. So I put that in as a constant, 3,000 meters, because at t equals 0, where it starts, it's 3,000 meters away. So that's that. It's going to be the velocity, 2,000 times the cosine of 60 is the velocity in the x direction. Ooh, almost. I got a minus. This one is headed in the negative direction. So that's a little different twist on this one. It's not fired from the origin, and it's also traveling in the negative direction. I can take this, and in principle, I solve for the time. Always solving for the time in one, substituting it into the y equation. Get that. From this, I've got a bit of a mess here that I could have simplified, but I guess I'm going to do that here. I'm going to set these two y's equal. That's where they're going to intersect. This equation and this equation are set equal. And then we want to solve for the place where they're going to intersect. We're going to start by solving just for the x of that position. And x should be equal, since they're going to all intersect. x1 is equal to x2 is equal to x. And of course, y1 is equal to y2 at that intersection. So if I take x1, what am I doing? Okay, I'm solving. I'm setting these two things equal. This one. This is a function of x1. This is y1. We're going to set y1 equal to y2. This is a function of x sub 2. What I can do when I set these two things equal, I'm leaving some steps out here. These are steps you can do. A students, if you're looking to get practice before the exam, you can do this. I can delete these subscripts, since we're talking about the same x, whether it's x1 or x2, or just call it x. So I just stuck it in as an x, dropping these subscripts. And now I've really, when I put these two things together, I'm going to get a simplified. It's going to be a quadratic. I've got an x squared term here and an x here. I'm going to have an x. This, when I expand this, it's going to be also give it a constant. I'm going to have some constants here. You can see it algebraically. It's going to get a bit messy. I'm just kind of putting out the pieces here. And we can then solve for the x. Now I did quite a bit of work from here to here when I set these things equal. I think it's accurate. I come up with this as a result, and I want to solve for the x. The x would be the point right below where this thing is going to hit. Same x is up here. And I came up with 2170 meters. That's going to be the distance out here. So I guess I've got it drawn a little off. It's a little back here. And we can get that position. And then I can go back and get the time, t1, the time that it takes to get to here from this one. That's going to be the, in the x motion, the 221.7, how far do I need to move? Also divided by the velocity in the x is going to give me the time that it's going to take to get there. Do the similar thing for this other equation, solve for t2, and that's, well, you can see what I'm doing there. I've got a little bigger mess because of this other thing is not fired from the origin, but it should make sense to you. That's going to be t2. And so we've got t1. It takes this projectile 2.36 seconds to get there. This one takes 0.98, less than a second to get there. And so as far as the firing, if cannon 2 fires after cannon 1, they can hit. And we need to take the difference in these two, the delta t between t1 and t2. Whew. Okay, hopefully you followed that a little bit. I put this on here. I would say don't waste a lot of time depending where you're at. But if you're feeling confident and you want to give a shot at this, you can do it. And then, did I? Oh, I didn't. Okay, so, okay, again, now this not quite as scary for most students when you start to put in numbers and then we can generate these equations. But keep in mind the kind of the big picture, what we're doing with this, and it's hopefully not too bad. Yeah.
So we said they start easy and then make it harder. So like what?
Oh, the exam. Okay, now these something like this would be the hardest one on this first exam.
Okay.
Now you're thinking about for the whole course.
No, just the first.
Okay, the first exam. Yeah, you're gonna have 5 questions, and they're gonna start off easy. So typically, like this one would kill most students. Okay, so maybe you get some partial credit here, but most students wouldn't get it. But there will be some that do. You know, math whizzes. They can, yeah, no problem, I got it. Anyway, so. The big thing is that, you know, you maybe get confronted with these things like I'm confronting you, and then after you get over it, it's not quite as scary as it looks at first. Okay, now kind of going back a little bit, it's kind of a review. I did all these things here. I'm going to do something very similar. One of the hardest problems to do as far as projectiles is one that conceptually seems pretty simple. If you know you have some target off there that you want to hit, maybe it's up in the hills a little bit, and it's got like coordinates, an x and a y, and you want to hit it, and you've got some gun that fires with some velocity. The natural question is, well, how do you aim this thing? What angle do you fire it at so that it hits the target? So, I mean, that's probably the most natural question to ask. In terms of doing the problems, it's the hardest question to do. You've got one that's in the homework. How about the dive bomber problem? It's coming in. Okay, you had to solve for the angle that that guy is coming in at because he's going to release the bomb at precisely that same angle. So, wow. Trying to find the launch angle. Okay, now a lot of this is repetition. I know it's just all this stuff up here. The idea that the x motion, okay, is typically we just do this for the projectile. Typically we solve for the time, And then we go into the y equation and substitute that time in. So this is what I'm just doing this symbolically. Again, I'm going to put that in here. So this is very similar to what I was doing earlier. I just want to collect some terms here. Again, this is going to give us an x squared term and an x. So this is going to generate the parabola. But rather than do that, let me look at solving for the angles. So let me just put this up in here. So again, I start with y, substitute this in for x. So it comes in here. Cleans up a little bit. The v naughts cancel. The sine over the cosine is the tangent. I've got an x. I've got some, when I square this, I've got some constants here. I'm going to keep the x squared over here, and the g here, and the 2, and the v naught squared. And the cosine I'm going to put out here. So previously I'd put the x over here and this inside, but let's put this over here. Okay, now what I want to solve for is I want to solve for theta. Pretend I've got everything else. I know what g is. I know what this gun will fire with what velocity. But now I need to get that angle. What angle? How do I aim this thing? So I can simplify some things, and here's a trick in doing these, and it does require a bit of a trick. If you look first at this, you might generate this and say, well, yeah, I got that, but how am I going to solve for theta? I got a tangent of theta there, I got a cosine squared of theta here. What am I going to do? Here's a little trick, trig identity. Of course, you've seen this one. 1 is equal to sine squared plus cosine squared. If I divide through by cosine squared, this goes to 1. This is the tangent squared, and it's 1 over the cosine squared, or secant squared if you want. What I'm looking at is this thing, rather than rename it secant squared. I'm going to take the tangent squared plus 1 and put it in for that expression. Now at least I've got things simplified a bit. Let me group some of these terms. I know they're all floating all. Consider that all of these things are really from the initial conditions. You know, you've got gravity. You want to hit some mark x. So if I know the position of that target over there, the x and the y, I know what the x value is. I know what the velocity of the bullet is. I can stick those into my calculator. I can generate a number here. Tangent of, again, I've got x here. I'm going to know what that x is. I have to know what the target is. I know what its x and y is. In fact, I can use the y here and the x here, as well as the initial velocity. All of this are going to be constants. So I put in red really what we don't know. We need to find the angle. And this is tricky. We've got this, but again, this stuff in blue is stuff you should be able to just punch into the calculator from what's given in the problem. And then it's a question of solving for theta. Now, once you get it in this form, look at it. We've got a tangent squared. We've got a regular tangent. Here's where we want to use the quadratic formula to our advantage here. We want to consider that this is some number, the tangent squared. We can solve for that number with the quadratic equation, where these A, B, and C, these are going to be these constants. Okay? And then you can generate once you get the tangent, then you can take the arctangent, and then you get the angle that you're firing at. So all of this is what you need to do in that dive bomber problem to actually solve for the angle that he's diving. So if you're having some trouble with that, or maybe oversimplified the problem in your head, this is what you're going to need. Now, Dr. Young generally doesn't ask these simply because, wow, what a mess, huh? Yeah, you had, just a second, you had your hand up?
I think he was first.
Oh.
So if we have two answers for the quadratic equation, how would we pick the right angle based on?
Oh, okay. Actually, both of those will give a solution. Think back to the range formula. There's a number of slides back where we had two answers where the projectile would land. So if I have a particular target, there's two angles that I can fire. I can fire at a lower angle or I could fire up. And both of those thetas that we get out of this solution are going to work. Yeah.
So I thought I remember in some of the homework problems that we weren't given theta and we weren't given initial velocity either. But it may be that we were given x and y so that we could get the angle by the Pythagorean theorem or by the trig identities.
Okay. I'm trying to think right now what problem you might be thinking of. You can.
I can't remember, but generally, if we're not given the angle, we're going to be given the initial velocity. Would you say?
Yeah, you've got to have. Obviously, you've got to have some information. We need to know. We need to know some information about the speed of the bullet. If I don't know that, then it could land anywhere, really, because you think of firing the gun. I don't know what the velocity is. Is it just going to fall out, or is it going to really take off? So I think you'd definitely you'd have to have enough information to do the problem. And so anyway, this is the nastiest they get. And again, if you need this for the dive bomber problem and whether he would do this on the exam, you might judge, say, not too likely. Okay? Yeah.
Why do you have to use this whole expansion? Why can't you just use the original parabolic motion formula that's comprised of...
Oh, okay. You could, just rearranging the terms. Partly I did this just kind of reiterate what we have done. This is very similar to what that is. The other one, what I did is put this inside. We took the x squared out there. So it's just putting those, and then that is that same one. So it's not like this is a whole big separate derivation. Maybe that, good, thanks for bringing that up, because essentially this whole argument is paralleling what that is. I just really grouped different terms from that idea.
So this is just solving it using the quadratic formula versus working it all out using the arc, eventually the arctan to find it.
Oh, yeah, well, we do need the arctan once we get that. We're solving really for the tangent of theta, and then we need the arctan to get the actual, get that angle.
So the prior step to using arctan is simplified.
Yeah, just,
Compared to the parabolic motion.
yeah, okay. Okay, it's definitely kind of strange the first time you're seeing this, yeah.
Is it possible to find the angle using the velocity in the y direction, substituting the t inside of the second equation, and then that to find theta?
Okay, well,
Using the velocity equation instead of the position. Can you substitute the t from the x motion and then use that to find theta?
I think that's going to be dependent on the angle also. So I mean, you've got, this is t, so you've got a cosine in there. So you're going to have a sine and also a cosine. I think it's still going to be tied up in there. We could maybe play with that, but I don't think, in terms of if you do need to solve for angle, I haven't seen a simpler way to do it, you know.
You use that, the velocity one, and then plug in the time from the x. When would we use the second equation?
Oh, this one? That would, of course, give you the velocity in the y. That would in general be true. So if you took this time and substituted it in here, that would be an expression for the velocity as a function of position. Because when we put in this for time, we've got an x there. And so you're going to have an x as well as an angle. So again, we're just dealing with more variables. Okay. Okay, I don't want to scare you too much. There is, I think, just one other topic that we need to touch on. Is circular motion, and that's motion in 2 dimensions as well. Let me just kind of play a little thing with centripetal motion. I have trouble with this. Okay, let me start off here. Let's say we're going around a circle. Ooh, is that still playing? Okay, I've got a clunky thing with these animations here. The idea is if you're going around here, the velocity is always tangent to the curve. And so this would be some time, let's say delta t, as it goes through some little angle. These velocity vectors are going to sweep. This is going to be perpendicular to RF. This is going to be perpendicular to the initial in R initial. And if we go a little further, let me just displace these two vectors. Okay, so just kind of moving these. Okay. And come off here. This angle, can you see that this angle would be the same as this angle? Just similar triangles. Again, the velocity vectors vary between in their angle. They're going to sweep to the same angle that this sweeps through. We've got, now I'm starting off here with these two velocities, final and initial, going to be the same value, meaning that it's going to be going around this circle at a constant speed. And when we do that, let me go a little further here. Okay, this V final minus V initial is really, this is really delta V. That V final minus V initial would point in that direction. Also that delta R, the distance here, is going to be the difference between these. Going to be this is kind of the displacement vector as it goes from here to here. Consider that we're going to be kind of arguing and taking the limit as delta t approaches 0. This is going to get much narrower, and this is going to fit the curve better. And this angle is also going to get narrower. And so these two, again, are going to be similar triangles. And with the similar triangles, we can just write a simple proportion. Where are we here? Get this right here. Yeah, delta R is to R, as delta V is to these velocities, V. Of course, these radii are the same magnitude, different directions. These velocities are the same magnitude, just different directions. So I'll just call it delta V over V. So I'm dealing with just magnitudes here. And then as we go through this, it's getting kind of clunky here. Yeah. Yeah. Okay. Here's the ratio of these two. Maybe I'll hit the play button, see if I get through this all right. Okay. And then just solving for these things, and then dividing by this delta t. Again, we're going to take the limit as delta t approaches 0. We're going to have a V over R, and delta R over delta T, that should be just the velocity. And so we're going to end up with a V squared over R. And that's going to be, yeah, again, V squared over R. And so if you're wondering, well, if you're traveling for circular motion, we keep using this V squared over R. This and delta V over delta T is what we'll call the centripetal acceleration, again in the limit as delta T approaches 0. But that's going to be V squared over R, and that applies for any kind of circular motion. If you're drop this point later, but so that's this idea. Let me take it in a little further here. If I do, wait a second. Okay, the acceleration is going to be in the direction of delta V. Delta V and is going to be just delta V divided by delta T is the acceleration. It gets its direction from delta V, and it's always going to be pointing into the center of the curve. And let's see, I think, and then That's all I want to show on this one. Broke this up. Okay, so let's look at a little more advanced case. Suppose it's also speeding up. So we have V initial coming over here, but V final is going to be greater, so it's picking up speed. The previous one was they were traveling at the same speed. So we've got this V final and V initial. And so if we try to pick through this, let me, got to get this better. Okay, so this really shows that delta V is off this way. Since V final is greater than V initial, it points off at an angle. And therefore, the acceleration is also going to point off at an angle. Come on. Okay, and what we'll do is look at this acceleration, or delta V, in kind of two terms. One that's in a change in the centripetal direction, pointing into the center, and one that's going to be off in the tangential direction. Now, again, this is the limit as delta t approaches 0. So this is going to squash down. Delta t, this is going to gets smaller, and these are going to become closer and closer to right angles, and will become right angles, if you can picture that in your mind, as delta t approaches 0. And that will be true for the accelerations. There will be a main acceleration this way, and we can kind of think of components of that acceleration as acentripetal, a centripetal term, and also a tangential term. The centripetal term is responsible for changing the direction. The tangential term is for the changing of the velocity. Now, the way we'll usually represent this thing is, let me see, I think I can just hit play here. Is it going to go in from? And we'll place these vectors like this. Okay? And usually what we have here, if we're dealing with circular motion, we're going to say, let's say the acceleration's off at some angle here. What we want to do is break it up into components, a tangential component and also a centripetal component. So what we want to do is take, and imagine a little box we put around this thing. These two components need to add up to be the acceleration. And again, a tangential is going to be responsible for this thing either speeding up or slowing down. The centripetal part is for changing its direction. It does not speed it up or slow it down. That's always the tangential term. Okay, yes?
Is radial and centripetal acceleration the same?
Oh, very good question. Yeah, this is coming up. The centripetal acceleration is what we call center seeking. That's what centripetal represents. It is into the same direction. Now, I know Dr. Young kind of uses them almost interchangeably because we're primarily interested in absolute value for it. We always know the acceleration of the centripetal has to be directed into the center. Now, if you're wondering about when it says the radial acceleration, we're talking about almost the same thing. The r-axis, think of like the x-axis. We say, okay, x goes that way, it gets bigger in that direction. What direction is I hat? It's in that direction. Now we can play the same game with the radial axis. The radial axis would be, this would be 0, and then this is going out. Out is positive. So we even can put in a unit vector, r hat, and that points in that direction. Now the acceleration, though, bottom line, is coming into the center. So a radial is going to be a negative v squared over r if we're watching the signs carefully. No, I know Dr. Young kind of uses them almost interchangeably and doesn't make a big issue of this. And for our purposes, primarily, we'll just do the absolute value. So virtually, we can consider them the same thing. But there is a technical difference. And
Which one would be in the absolute value if we were talking?
I would put it acentripetal because this is going to be a positive quantity, the number for it. And then in terms of its direction, we'll put the direction in. That's how we want to handle it as far as vectors. Determine what direction it should point from the physics of the situation, and then just say, oh, and by the way, its magnitude is v squared over r. Okay? So this is kind of the basics of it. Let's see if we can put it to work. A lot of these problems, it's kind of coming at the end, and people are just kind of, but the problems aren't too bad. I've got one that's kind of bad. Okay, here's a baseball is tied to a string and twirled in a circle as shown in the diagram. If the speed of the ball is 5 meters per second and the acceleration vector is 9 meters per second, or 9 meters per second squared, and 55 degrees from the velocity vector, what is the radius of the circle and at what rate is the ball changing its speed? Okay, so the idea is this acceleration vector points off at an angle. He's telling us 55 degrees from the velocity vector. So the velocity vector is there. 55 degrees would give us the acceleration. From the velocity vector. Okay, and he wants to know what is the radius of the circle and what rate is the ball changing its speed. What we want to do is take that acceleration vector and break it up into two components. And this, of course, could be anywhere on the circle, and these right triangles are rotating. Essentially, you want to put a little imaginary rectangle around the acceleration. So the acceleration lies along the hypotenuse of these little right triangles that are generated. Of course, this angle is 55. This angle is 55, or a lot of ways you could play with this. And sometimes they state these problems, they give this angle instead of this angle, so that's not always the same. But the idea is this acentripetal, pointing into the center, is going to be the magnitude of 9.8 times the sine of 55. Now, we've got the sine of 55 is the side opposite, is going to be this, and that should be the same as the centripetal acceleration pointing into the center. So a times the sine of 55 should be acentripetal. Okay, and so I get an acceleration for that in meters per second squared. But we also know, as we've looked at here, that acentripetal should be equal to the v squared over r. Now the v we're talking about is really at the tangential velocity, how fast it's traveling. And that's part of the question here. What is that? He does tell us what that is. It's 5 meters per second. So we go ahead and put that in for the tangential velocity. But he wants to know the radius of the sphere, or of the circle. So we've got all of these numbers here, and then we could go ahead and solve for the radius. He's got 3.39 meters. And then for the tangential acceleration, that's going to be this one. We're going to want that acceleration is the side that's adjacent to that angle, so that would be the cosine. So we're going to have 9 meters per second times the cosine of 55 degrees. And sticking the numbers into the calculator, we get 5.16 meters per second squared. This kind of is the rate the ball is changing its speed. So he's kind of cryptic in the way he's answering that. It's kind of like Jeopardy, where what rate is the ball changing its speed? It's really the question, what is a tangential? It's going to be this, the rate the ball that's changing its speed. So this would be an answer, and then he also wants to know the radius of that circle. So that's a kind of straightforward one that this is typical of the ones that he gives. Sometimes he gives ones that are a little, he decides I'm going to have to add a little bit. We got to do a little more with vectors here. So let's see if we can make this just a little tougher. We're going to have a rock spinning in a circle with a radius of 1.2 meters. Okay, when the radius makes a 45-degree angle with the vertical, so that's right where it's here, and the rock is on its way up, so I guess it's spinning like this, and it happens to be going up like this, on its way up, the acceleration vector is whoa. And he gives this in terms of I and J notation. Okay, so that is okay. And then he's asking kind of the same. What is the speed of the rock? Okay, and what rate is the rock slowing down? So really, there's kind of two questions. Usually, hint, find AR and AT. So he's got that. Now, doing this is a bit miserable because of the way he stated this. He's got the acceleration, this is how he states it in the problem, it's a minus 25I plus 20J. So if I want to look at that vector, and we're talking about this point when rock is going up, but the acceleration, he's got a negative in the I, so it's back this way, positive in the J, so it looks like it's pointing back in this direction. Now, I need to get it in terms of a tangential and a radial components. So this looks a little strange. So what I'm going to do is I'm going to break this up into this little rectangle here. I mean, right triangle, excuse me. Going to be that. And I want to get the angle here between the acceleration vector and the horizontal, so I can get that sense of where it's at, and I'll show you what I'll do with that in a minute. But to solve for that angle, I would do the sine is the side opposite, that's 20. I'm going to do this absolute value, and then in the x direction, which is negative, but we'll do it absolute value, is 25. And so I look at this, and I see this is 38.66 degrees in here. Now, he told us this angle was 45, and can you also see this right triangle? This whole angle should be 45, hopefully. And that's kind of guiding what I want. I want to get the angle between the radius of this thing and the acceleration. So I would like to get phi so I could break that into components of tangent and radial. Okay, this definitely slaughtered a lot of people here. So he takes this angle, and that angle plus phi, these two should add up to 45. And so, a little quick math here, we get this angle phi is 6.34 degrees. Okay. Also, the magnitude of the acceleration, a little Pythagorean theorem there, I come up with what the acceleration is. The acceleration, the x component and the y component. When I square them and add them and take the square root, I can get this. Okay, this is complicated enough, and so I kind of started again with the picture. The acceleration is still off in this direction, but I want to put it in terms of components that are atangential and acentripetal. So that, and now I know what this angle is, 6.34 degrees. So now once I have that, I can take that and get acentripetal. That is the side that's adjacent to that angle, so I use the cosine. A cosine of theta is this, and sticking in the numbers, the acceleration was 32. I know the cosine of the angle that I know, and I can get acentripetal, so that's not too bad. And also, acentripetal is equal to v squared over r, so both of these have to be true. And so I can solve for v, and the speed of the rock going up is got to be this. So that's the speed that it's traveling. And then we can also get the rate that it's changing speed. That's a tangential. That's going to be a times this side here is the side opposite phi, and that's going to be the same as a tangential. So that's going to be a times the sine of phi, or 32 times sine of this, and we can get then a tangential. I will get a negative. It's back in this direction. I got that from the fact that the acceleration is off that way. And since it was traveling this direction with the tangential component in the negative direction, that implies the rock is slowing down as it goes up. Okay? Now this is the hardest kind of problem I've seen him do with this circular motion. I thought to give it to you here. It's got a lot of practice here because we have to take this thing, break it up into components, and rectangular components to get actually at the acceleration in these angles. And then ultimately, when I do these kinds of problems, I want the acceleration back either this way or out in front, and then get these centripetal and tangential components that are going to be at right angles. The test also is these are components, so if you add these vectorially, you should still get the acceleration vector that applies to there. So I hope that works for you. Okay. Again, this is a nasty one, but it does have some things in there that are worth looking at. And wow, good luck. Okay, so okay, I'll stick around for a while if you anybody's got questions that they've been working on, homework, and I'll deal with more questions. Okay. Right now, let me shut off this camera and then.